Okay, so this is the week number one, part four. Let me continue to tell you the compound semiconductors herein. Let's take a look at the not atomic, the crystalline structure of compound semiconductors. So basically, these compound semiconductors, for example, gallium arsenide 3,5 compound semiconductor, has exactly the same shape of the crystalline structure or diamond structure of silicon atoms, silicon crystalline material. So again, 3,5 compound semiconductors like a gallium arsenide is exactly following the same, you know, material structure of silicon crystalline material. In other words, we have learned that crystalline silicon material has diamond structure, but then your follow-up question is, can we still use the word diamond structure for 3,5 compound semiconductors like gallium arsenide? The answer is no. So we are using another word phrase, zinc blende structure, as I have noted here. Zinc blended structure. So what is this? Zinc blende structure has been drawn in this unit cell. So basically, in terms of shape or in terms of where the atoms are placed for unit cell, the zinc blende structure is identical to the diamond structure. No difference other than the atom. Here, arsenide. Here, white colored one, gallium. So gallium arsenide 3,5 semiconductor, the ratio of gallium to arsenide is 1 to 1. Therefore, for each spot you know for the I'd say seat for atoms, once this seat is filled with arsenide, another seat should be filled with gallium. So alternatively, gallium atom or arsenide atom uh, filling up of with are filled with us each seat. Okay? So alternatively, gallium and arsenide atoms are placed here and there. But in terms of the position and arrangement of seats and space for gallium or arsenide atom to be filled in is very identical to the diamond structure. Okay, right. Now, in this movie clip, let's put more focus on the crystallographic notation. So as you have learned and as you have guessed, the diamond structure or zinc blende structure is quite well patterned and well ordered. Therefore, it is hard to tell which side is front, which side is back side. Depending on where you are standing up, whenever you are looking at the crystalline material, you can claim that this is a front end, front uh, plane. That is a left hand side plane, and that is center side, and the diagonal line looks quite different from the diagonal lines that my friend is looking at. To avoid this type of confusion, people has developed a notation that is named as Miller indices. Okay, so Miller indicates a person's name. The person Miller has developed this crystallographic notation. So let's take a look at some details on crystallographic notation. On the left hand side, you can see that a single unit cell and X, Y, Z axes are drawn together. So say this corner is now placed on the origin, and let's take a look at this plane. Since you are listening to my lecture, and I have indicated explicitly where the which planes that we are looking at. So we know, take a look at this plane. So this plane is understandable. But for friends who cannot access to this movie clip, then it's hard to imagine which plane are you talking about. Okay, so here is Miller indices. Now, what if you're interested in this front plane? Uh, what is the right expression for this red colored plane? So steps to get Miller indices is as follows. First, take a look at the x, y, z intercept of the plane that you are interested in. So since we're interested in this plane, so what is the x-intercept of the plane here? What about the y-intercept? Since this plane is running in parallel with two y-axis, so the y-intercept is infinity. What about the z-intercept? Since this plane is running in parallel to z-axis, therefore the z-intercept is infinity. So only x-intercept is here. So what is the value for this point? Since one side length is indicated with lattice constant. For silicon crystalline material, the lattice constant was 5.4543 nanometers. All right, just to make our life easier, let's say that the x-intercept is simply a. So now x-intercept is a, and y-intercept is infinity, z-intercept is infinity. And following the details of how to get Miller indices, let's do this. Take uh, take 1 over a, 1 over infinity, 1 over infinity. Okay, and what about the value of 1 over 8? 1 over 8 is simply 1 over 8, but 1 over infinity is corresponding to 0. And 1 over infinity is corresponding to 0. Okay, then these, these three different numbers should be reduced to three integers. Okay, so 1 over a is not integer. So to make it integer, let's multiplying a for those three numbers. So afterwards, times a times a, then we are gonna end up with this three number 1 0 0. Okay, so 100 is the intrinsic number for the plane that we are interested in, front side. So I said plane. So Miller indices said that to indicate plane, you should use small parentheses. Okay, so 100 use parentheses. So here notation, small parentheses, and use the number HKL. So in this specific example, the H was 1, K was 0, L was 0. Okay, so interpretation, the meaning of this notation, small parenthesis HKL indicates a crystalline plane. So since we are interested in this plane, so this plane is named as 100 plane. Okay, so now you can now uh, tell your friends who are not in your room the exact name of the plane that you are interested in. Okay, so take a look at the 100 plane, then you can communicate with your friend. Okay, this is the main part of the Miller indices. So again, when you're estimating the Miller indices for the plane that you are looking at, try to get the x, y, z intercept first, and then take a three integers. Okay, then you're gonna have a HKL value. So for your practice, let's do one more thing. What about this right hand side plane? X-intercept infinity, Y-intercept A, Z-intercept infinity. Take 1 over the number that you have, then 0, 1 over A, 0. And we should take an integer, so 0, 1, 0. Now we are talking about the plane, so use a small parenthesis. Then you can say that this plane is 0, 1, 0 plane. Okay, so herein you can see three different examples. So here, as we have just done, this plane indicates a 1, 0, 0. What about this area? X-intercept is A, Y-intercept is A, and Z-intercept, this plane is running in parallel to Z-axis, so Z-intercept is infinity, so A, infinity. Take an inverse of it, then you're gonna end up with 1, 1, 0 with a small parenthesis. So now this plane indicates 1, 1, 0 plane. Okay, let's do the last one. What about what is the plane number? Um, intercept A, Y-intercept A, Z-intercept A. So A. So take a smallest integer, so 1, 1, 1, with a small parenthesis. That's it. So now you can say that this plane, take a look at this plane. No, this is not correct. You can tell your friend, take a look at 111 plane. Then your friend can take a look at this plane. All right. So what is how can you use these Miller indices uh, once you have a job in AI? Maybe whenever you are placing an order for silicon wafers, the vendors will ask you which plane which cut or which direction of silicon wafers do you want to purchase. So most likely this plane, the top surface of silicon wafer is 100 or 110. So it depends on the cost. Okay. Anyhow, silicon wafers are usually and generally cut along a 100 plane with a flat, most likely to save or to fabricate more chips, DRAM than the dies and chips here. Uh, Current state of the art CMOS fabrication uh, line would prefer to use notched silicon wafers. So only small any amount of silicon uh, has been lost, and we can fabricate more die die chip. So let me tell you some brief concept of die and chip. So for given wafer, uh, once all the fabrication steps are done, then we are gonna cut the wafer using diamond saw at x and y x and z y direction, and this part can be used as a raw die. Okay, so how many dies we can fabricate from a single wafer is very dependent of cost. So to reduce the cost, people in device in fabrication process engineer like to prefer to have a much more number of raw dies from a single wafer. So what is the way to increase the total number of raw dies? Well, the simple idea is to enlarge the diameter of the silicon wafer. So for the past maybe a few decades, the silicon wafer size was 4 inch to 6 inch to 8 inch, currently 12 inch diameter, 12-inch diameter. 12-inch is corresponding to the 300 millimeter or 30 centimeter long diameter. This size is hard to imagine, then try to make a fun order to Pizza Hut or Mr. Pizza. Definitely you should order a larger size, not regular size pizza. Then you will have a fun experience how big the current cutting edge silicon wafer is, which is exactly corresponding to the larger size of Pizza Hut. Okay? So 300 millimeter or 12-inch wafer is now mainstream. However, to reduce the cost of fabrication fee, 8-inch market is still alive. Okay, and for R&D purpose, 6-inch or 4-inch is you know wide enough. Anyhow, remember the 10 nanometers, 1Z nanometer DRAM NAND flash is currently fabricated with a 12-inch, 300 millimeter diameter size, 300 millimeter long silicon wafer, right? So the bigger the substrate is, the more the raw dies are. Okay, so in this slide, you will see how the silicon atoms are placed depending on the direction. Let me go back to the Miller indices again here. Let me explain more. So crystalline direction. So direction means, say that here, we have learned to indicate the plane number 100 plane, but we are saying that in some cases, we would like to say the direction of this plane. Then the direction means the vector normal or perpendicular to the plane, okay, indicates the direction of this plane. The crystalline direction is quite well matched to the vector analysis in your calculus class. Okay, so calculate the vector of this one. Well, this is very simple. Just pick up a certain point within a plane and calculate the vector value. So in this case, this distance is a, right? And the yz direction is running in parallel to this vector. So a 0, 0. Okay, and take a simplest integer. So we can say that 100 direction. But instead of using small parentheses, we are using a bracket, okay, to indicate direction. All right. Um, Whenever I'm teaching this Miller indices, always think about this one. This is a small parenthesis. This is a large bracket. And this is a plane. This is a direction. So in Korean word, so I'm sorry to use a Korean, Korean alphabet, but you may see you're very familiar with this simple Korean alphabet. So plane in Korean alphabet is a myeon. Okay, the direction indicates the 방향, or just simply take the first one, 방. Okay, 방 is exactly kind of room, but just don't forget the room. Herein, the direction in Korean word the 방향, so 방. Okay, 방면, here 면, 방. And this is a small in Korean so. This is a large in Korean that. So Miller, whenever you are hearing the Miller, you may think of the yellow colored one, soda. You know what I'm talking about. Yellow colored, soda water. So this Miller and somyeon. Somyeon indicates a noodles. Okay. Whenever you're drinking the Miller stuff, you may always need a side dish. Maybe definitely the main representative of side dish is noodles, right? So somyeon in Korean. So mainly this is somyeon and okay, and myeonbang. Myeonbang is a kind of sounds like a myeonbal. Bang is quite similar to the ball. Number mean indicates how flexible, how tangible, how to say uh, how resilient. I don't know the exact English word to express how. Oh, this is the word. How fresh the glass noodles and ramen noodles are good, right? How fresh it is. So somyeon and myeonbal. Okay, then you may uh, memorize whole whole view of this table. So the Myanmar. Okay? Miller. With Miller, may always imagine the side dishes, homyeon, and how fresh the noodles it is. Okay? Right. Okay, so here is a summary. So we have learned the crystalline silicon. Uh, Single silicon atom has four outest electrons. Okay, so I'm talking about the atomic number of silicon is 14. So it has 14 electrons. However, two electrons are running and limited in a first orbit, and the other four electrons are limited and closed and running in the second lane, which is corresponding to the 2s 2b orbit. 2 and 6 are split into these separate lanes. And definitely here, the primary number, quantum number is 1s orbit, and there are only two states available for those two electrons. Okay, then the last one is a 4, right? So those four outest electrons are running in 3s and 3p orbits. In 3s, 2 electrons. In 3s, 3p, 2 electrons are filled in. Well, definitely up to 6 electrons can fill in this 3p, but the number of electrons left is 2. So these four electrons are now hybridized 3sp orbit. Okay, so those four valence electrons and four electrons will be freed out, and they are the main characters to throw current in DRAM, NAND, and transistor, and PN junction, diode, all the electronic components. Whenever you are talking about how the current is flowing, so always remember the four outest electrons of silicon atom will be the main one. Okay, and the next one that we have learned is how the silicon atoms are placed to build up the crystalline silicon materials. Again, crystalline means the silicon atoms are placed under a regular, under a rule. So we have learned the rule. For 8 corners, we can place a silicon atom, and on 6 planes and 6 faces, we place silicon atom. Well, definitely half of it is included. We need a unit cell. And in a unit cell, we have a 4 diagonal lines, and each diagonal line at the position which has 1 to 3 ratio, silicon atom is placed. And we have calculated and counted how many effective silicon atoms, again, effective number of silicon atoms are included in a unit cell. It turned out that 8, right? So once we can calculate the cell volume, unit cell volume using a lattice constant, which is 0.543 nanometers, then we can end up with the number of 5 times 10 to the 22 atoms per cubic centimeter, which is the atomic density of silicon atom, silicon crystalline material. Okay. Afterwards, we have learned the crystallographic notation. So, yellow colored soda with a side dish and noodles, how fresh it is. So, Miller indices can be used to designate, to indicate which plane, which direction you are talking about within a crystalline material. So, in that sense, Miller indices has been widely used crystallographic notation. Okay, so that's all about the lecture note, the very first lecture note. And in the next movie clip, let's learn about some more on solid state physics. Okay, see you next. See you soon.